All right, so your bell ringer today asked you to take a look at this function y equals 1 over x minus 1. We've been looking at rational expressions, so this right here is a rational expression. This is the related function of that rational expression. So we're going to investigate a couple things here. The first thing it asks us to do is to complete this xy table. So given this list of domains, x equals -2 through 4, find the corresponding ranges or outputs using this function. So all we're going to do is we're going to evaluate this function for the different values of x. So let's first evaluate where x equals -2. If we do that, we get 1 over -2 minus 1, which equals 1 over -3, or -1/3. Now we'll evaluate where x equals -1. We get 1 over -1 minus 1, which is 1 over -2, or -1/2. Let's evaluate x equals 0. We get 1 over 0 minus 1, which is 1 over -1, which is simply -1. When we evaluate x equals 1, we get 1 over 1 minus 1, which equals 1 over 0. Now, let's pause for a moment, because this is significant. If you've ever in your calculator tried to take a number that's non-zero but divided by 0, it's going to say error, domain error, divide by 0 error, depending on what calculator, it'll tell you something different. But the important thing to recognize here is mathematically, we say that you cannot divide by 0. What this expression is undefined. Okay, so when we try to evaluate this function for the domain x equals 1, we get that makes the function undefined. Therefore, there is no corresponding y-coordinate. There is no range for that domain. So I'm just going to put a line here to indicate there is no y value when x equals 1, because again, that makes the denominator 0, which makes this expression undefined, or the function is undefined. If we keep going with x, the x values, we get 1 over 2 minus 1, which is 1 over 1, or 1. 1 over 3 minus 1, which is 1/2. And 1 over 4 minus 1, which is 1/3. Okay, so now it asks us to plot these points on the coordinate plane to the right. So we're going to plot each of these as an ordered pair. So -2, -1/3, and obviously I'm having to estimate because I don't know exactly where -1/3 is on the y-axis. Next point is -1, -1/2, 0, -1. Now we won't plot any point for where x equals 1 because we don't know the y-coordinate. Again, we say that it is undefined, so we'll jump over here to 2, 1, 3, 1/2, and 4, 1/3. Before we move on, something I want to point out, I want to return to this idea where x equals 1. So we've already said that x cannot equal 1, but let's continue on with this pattern because we sort of start to see a pattern emerging here. As we're increasing the x values to a point, the y values are decreasing, but then we sort of jump up over here where as we're increasing the x values, the y values are actually decreasing. So let's keep going and pick a couple more domains or x values here to evaluate. So let's try 1/2. That's halfway between 0 and 1. So let's come in here and let's try evaluating where x equals 1/2. Well, if I evaluate for 1/2, I get 1 over 1/2 minus 1, which I can't simplify as is because I need to have like denominators when I add or subtract fractions. So I'll rewrite that as 1 over 1/2 minus 2 over 2, which equals 1 over -1/2. 1 divided by a fraction, whenever we divide by fractions, we can multiply by the reciprocal. So that's the same thing as 1 times -2 over 1. So that will give us -2. So when I evaluate for x equals 1/2, I get y equals -2. So let's plot that point. So again, that sort of is consistent with this pattern. As we're increasing x to a point, y is getting larger and larger and larger. So if we kept going, so let's try something even closer to 1. Let's try 3/4. Let's evaluate where x equals 3/4. Well, we get 1 over 3/4 minus, and I'm going to skip a step, so 1, but we're going to have to rewrite that as 4/4. That will give us 1 over -1/4, which again, if I divide by a fraction, that's the same thing as multiplying by its reciprocal. So we get 1 times -4 over 1, which is -4. So if I plug in, if I evaluate for 3/4, I get -4, which again, 3/4 down here to -4, is consistent with what we're seeing previously. As we increase x, y is getting smaller and smaller, right? The negative value is getting increasing though. So we're approaching negative infinity, right? If I picked a point so close to 1, like if I tried x equals 0.9999 minus 1, well, that's going to give us 1 over 0.0001. So tenths, hundredths, thousandths, 10,000ths. So that's actually 10,000. So at 0.9999, I would have to go all the way down to, sorry, this would be negative 10,000. And I could keep going. And if I got infinitely closer and closer and closer to 1 from the left side, right, I'm going to approach negative infinity. So I would go down here to negative infinity. So we get a graph that looks something like this. And if we did the same thing over here on the positive side, right, because we're sort of seeing as we're decreasing the x values, right, we're getting a larger and larger y output. So if we try something here between 1 and 2, so 1 and 1/2 or 3 halves, let's see, we get 1 over 3 halves minus 1, which is the same thing as 2 over 2. So we get 1 over 1/2, which is simply 2. So we get 1/2, 2. Again, that's sort of consistent with the pattern we see emerging here. And if we try something even closer to 1, so let's try 5/4, 1 and 1/4, we would get 1 over 5/4 minus 4 over 4, which is 1 over 1/4, which is the same thing as 4. So again, at 5/4, I have a point up here at positive 4. So if I picked, something just a little bit larger than 1, so if we picked 1.0000001 minus 1, we're going to end up with 1 over 0.12345 zeros, which is tenths, hundredths, thousandths, 10,000ths, 100,000ths, 1/1,000,000th. So that actually equals 1 million. So when I evaluate this function where x equals 1 and 1/1,000,000th, I get y is equal to 1 million. So I'd have to go all the way up here to a million, right? So and we could get even closer to 1. So as I get infinitely closer and closer to x equals 1 on this direction, my y values are going to approach positive infinity. So we get a graph that looks something like this. So what we see here is that I can't evaluate x equals 1, but as we make x closer and closer to 1, we approach positive and negative infinity. That creates this sort of imaginary line here. This line is known as the vertical asymptote. Okay? And a lot of times what they'll do to indicate where the vertical asymptote occurs, if it's in a function, they'll put sort of comma or semicolon, x does not equal -1. And I was telling you guys last week that sometimes we'll see where they'll write these expressions with something very similar. They'll put x does not equal 1. So in that expression, they're even indicating that this expression and the related domain are both undefined for this value x equals 1. There's also, just real quickly to note here, because this expression can never equal 0, right? It can get infinitely close to 0. If I said that x is 1 million, so 1 million minus 1 would be 1 over 999,999. So way, way out here at 1 million, I would be at 1,999,999ths, right? So extremely close to 0, but I can never actually get to y equals 0 because this expression can never equal 0. So there's actually a second asymptote in this for this function that occurs right along the x-axis where y equals 0. And if you haven't guessed it yet, this is known as the horizontal asymptote. Asymptote. Okay? So the key thing to point out here again, and what we're really getting at is we're going to start seeing a lot of expressions today where they're going to include this piece of information afterwards, where they'll say x does not equal some value, some number. All of that's indicating, all that's suggesting is that those values of x make the function or the expression undefined, and therefore they are excluded. And we're going to talk about some ways in which that is helpful or useful as we move on later in class.